Okay, welcome everybody for today's IA-50 commemorative lecture. So the lecture will be delivered by Professor Dipankar Banerjee. Professor Banerjee is an astrophysicist by training and is currently the director of the Aryabhatta Institute of Observational Sciences, Nainital. He had obtained his PhD from IIA Bangalore and then completed two postdoctoral tenures in reputed institutions, one from Armagh Observatory, UK, and the other from the Center for Plasma Astrophysics, KU Leuven, Belgium. So in June 2004, he joined IIA as a faculty member, and in 2016, he had become a professor. In December 2019, he had joined ARIES as the director of the institute. His main research interest includes multi-wavelength study of the solar atmosphere using ground and space-based instruments, diagnostics of solar atmosphere using atomic spectroscopy, providing observational constraints for solar wind and space weather, magnetic seismology, imaging and spectroscopic instrumentation, study of the long-term variation of sun using Kodaikanal and other digitized archive and space climate. He has co-authored more than 100 research papers that are published in renowned national and international journals with more than 2,000 ADS citations. He has been awarded with many national and international project grants, either as the PI or as co-PI of the projects, including NLST and Aditya L1 mission. He is associated with many professional organizations, International Astronomical Union, Royal Astronomical Society, Solar Physics Division of the American Astronomical Society, Plasma Society of India, member of ASI, and AOGS. He has become a fellow of the Indian Academy of Sciences since 2019. So it is with great pleasure, on behalf of IA-50 Organizing Committee, I welcome Professor Dipankar Banerjee to deliver his lecture, My Journey in Solar Physics and Where It All Started. Dipankar?
Yes. Okay. I'm audible clearly, right?
Yes.
I'm audible clearly? Okay. So I will. Yeah. Thank you very much, Aruna, for the introduction. I'm privileged to be part of this celebration. I'm a bit nostalgic today, actually, because it's such a privilege to be part of IA. And I think in today's difficult time, I feel that we are really privileged to get whatever we are getting now, and we have got for the last 30 years or so. So I hope this talk will be a little cohesive, because I'm really emotional to sort of ponder over my last 30 years connection with IA. So what I will try to do, I give you a flavor about the multi-wavelength study of the sun, which I have been doing, and I will also try to give you a flavor about what I feel quite strongly about this. Yeah. So it all started, with my mentors, and I have to first acknowledge, them, Professor Siraj Hassan, who has been my guru all along, and then my two other mentors who has actually exposed me to the observational science and bit of numerics as well. So Jerry Doyle from Armagh Observatory and Marcel Goossens from Center for Plasma Astrophysics, they have been continuously supporting, and that's me. And another person which I have to mention, who has really contributed significantly, even probably, my choice of solar physics as a career by his teaching and his textbooks and so on. So that's Professor Arnab Raichandri from Institute of Science. So it all started 30 years back, and I dig this picture out from a Facebook page of Professor Kochar, who posted this pictures few days back. And I guess you are able to identify the people standing in the back row. And I'm really And of course, Annapurni Ishwar, young, lanky Ishwar, and the ever hero Shujan in the back. And I must admit, those days, Professor Kochar in the first year was our mentor. And on Sundays, our canteen used to be closed, so we used to venture into his house. And he was a great host with his wife. And of course, there were also other people at that time. There were not that many. You could identify Ranganath Rao. He was also doing his PhD at that time. And this is Sahu, who used to come and work with, you know, uh, uh, here. But now he's a faculty in IOP in Bhubaneswar. Yeah, so he was working with Professor Bhaskar Datta at that point of time. Of course, I was married, and some of our colleagues were also married, which is quite unusual being a PhD student these days, I guess. We really enjoyed our life, and also I must say, our faculties were very friendly with us. This is again another classic example. Those days we were looking for site in the Himalayas, and there were several teams went to different parts of Himalayas. I was in Prabhuji and Bagare Sab's team, and we are in the train, and Arun was given the task of accounts. So he was still calculating what all we are spending. In fact, as you see, our hero Shujar in the front of the mall of Simla. And then, of course, there were adventures as well. On our trekking to Kalpa, we lost two of our colleagues in the late evening. And next day, we sort of, found them back from this house where they took shelter. So that's again our hero and Professor Bagare. So those were the days, So it's really quite fascinating to think about it. So what I will do is now I will time to time, talk about the science which I have been engaged in last probably 15, 20 years. I will not go back all the way to my PhD period because that was completely theoretical, and I just discovered from my PhD thesis there were hardly any solar images in that. So it was all analytical calculations and so on. So that was good for getting a early training in the theory. So essentially, I have focused on these two major problems in solar physics. The left image is from SDO, and then you see this hot corona. So how to explain this heat in the outer atmosphere of the sun and the solar wind acceleration. So this is a picture from Ulysses, which is also depicting a picture of the asymmetric solar wind of high solar wind in the higher latitude and the low solar wind velocity at the lower latitude. This is a picture during the minima. And again, when the sun is very active, then this overall picture changes quite a lot. So one needs to explain, these two major, problems. And I have mostly concentrated in my early part on the role of waves on explaining these two phenomena. And if you want to do observationally, then of course the question comes, how do you detect these waves through imaging or spectroscopy? How do you characterize their propagation through their propagation properties? And then if you have the waves, that's not enough. You need to damp the waves to get the adequate energy to hit the upper atmosphere. That means damping. So you have to find signatures of damping. So in my early career, I was bothered about the wave generation process, propagation process more from a theoretical framework. And later on, I focused mostly on the observational part. So I will probably talk about mostly in the observation. And then here also I will indicate that all this work I have been able to do in recent years is only because of my able students. So I have not done anything actually. All the work has been done by my students. And I hope I have just been able to give some ideas time to time so that they have now matured enough as an independent scientist. So this is my first student from the JAP program, Girjesh, who is a faculty in PRL. Now, so we looked at that point of time, whether we could detect, Alfvén waves or signature of turbulence in the off-limb corona. So if you focus on this kind of polar region, this is the typical expression for Alfvén speed. And if you want to calculate how much energy they carry, this is a simple expression from the linear mode analysis you can get. So what you need to do observationally is you need to have a way to measure the density in the atmosphere. You also need to somehow find this RMS fluctuation, which is because of the presence of the local turbulence or the presence of the waves. It can induce something in the spectral line. So this is what we did from a spectroscopic observation. So if you look at the line width of a spectral line, then there are different terms in the spectral line. So this is the red one corresponds to the thermal contribution. So if you are measuring the line width with a very specific ion, and then you have an estimate about its typical electron temperature, and then if you assume thermodynamic equilibrium, then you get an estimate about the ion temperature. You can estimate this thermal contribution. Of course, this is what is due to the presence of the either waves or turbulence, and the green one is instrumental width, which you need to know before the this particular spectrograph is in use. So that was the observational framework which were needs. So there has been efforts of non-thermal widths of spectral lines in the solar corona. It started in early 90s. There was a rocket experiment which first detected these spectral line variations with height. In fact, Professor Jagdev Singh also has done quite a few work on this from the coronagraph in Japan. And then we started looking at it with the first very high resolution spectrograph with Sumer. This is one of the spectrographs on SOHO. And this was my first observational paper, actually, this one. And the result, what we showed that time, that if you look at the polar coronal hole, then these boxes corresponds to the numbers of the observed numbers, and you see that the non-thermal width increases, but there was a indication that beyond certain height that there seems to be a decline of this increase of the line width. And these plus symbols were from a theoretical estimates that if you assume that there is a expanding flux tube, and if you have a linear Alvan wave, what is the kind of psi values you are expected to see on there. So as you can see here, that there was a little bit of a departure from this. So we, at that point of time, many years back, we pointed out that maybe it's a location where the nonlinearities either are taking place, or there may be an indication that the waves are getting damped beyond certain radius, maybe 1.2 and so on. Later on, this was sort of confirmed by another spectrograph, which was there called ICE on Hinode. This is the Japanese satellite. And then with multiple spectral lines, they seen similar results. So this was from a siliconate line, which was there in the Sumer spectrograph. And we also carried out a detailed study. Incidentally, in the polar region, you also see these extended structures. They're called polar plumes. They are normally of higher density and so on. And then within the plumes, you have the interplumes. Now, there is still a debate that whether it is the interplumes or the plumes are the accelerating regions for the fast solar wind, because now we understand that the polar regions are the source or the site of the acceleration of the fast solar wind. So these line width observations are important in that context. So the David Perez was again a PhD student in our observatory, although I by that time I was back in India, but he came here to work on his thesis work as well. And incidentally, this is the letter paper which I wrote. I remember from Pangong. I was doing the site survey 2 weeks. I was there in Pangong in December, and that was such a quiet and concentrating time. I could write this nice paper at that time. So then, of course, comes the question that when you observe on certain particular instrument, then there are instrument characteristics which could affect your result. So when in 2000, later part of the 2000, this joint observation started getting of a fashion. So this was a campaign which did with the SOHO and the Hinode spacecraft. Two spectrographs looking at the same region in the sun simultaneously at same time, and so on and so forth. So this was part of Gijesh's thesis. We worked at around the same time. This was followed by first study from from AIA. This is the imager on the Solar Dynamic Observatory. And we were actually, this is again a very nice example that probably from the AIA instrument, the first science result came from Bangalore. The AIA had the policy of open data policy immediately after the launch. And we were the first guys to look at the data and publish it. This paper was sort of done within 3 weeks, since it was a letter paper, and nobody objected to this also, even the instrument team. And there were nobody from the instrument team also. We sent our result. They said, no, you have done the work, excellent, and NASA exactly wants that. They want independently people getting access to the data and publishing in the top journal. So this is, again, a good example of the open data policy, what it can bring in. What Krishna did, AIA has many different channels. So it is important to look at simultaneously from different channels, which represents different temperature plasma. And when you see propagating waves, and if the wave properties are different, then you can characterize the properties of the waves in terms of the slow magnetoacoustic and so on, because slow magnetoacoustic waves, we know, are temperature dependent and so on. In fact, this also led to a sort of debate that these waves or these propagating disturbances, what you see in the outer part of the atmosphere, whether they're really due to propagation of waves or they are quasi-periodic propagation of flows. So this flow versus wave debate was really maturing at that point of time, because there was also a stereo spacecraft, and there was some American team. They started debating on that these propagating disturbances, what you see, are actually quasi-periodic flows. We continued this debate later on, and we said that there is a signature of waves and flows both. This is a further study which Krishna did. What we also found out that these waves seems to have different periodicities as well. So that means there are different components or different frequency component of these slow waves. And what was even more interesting, that even if you look at again this multiple channel here, this was done for an active region loop system. Here, one loop system and two loop systems are really indicated here. And there was a very long time series of 3 hours, and with the best possible cadence. This was again the beauty of the AIA instrument, and simultaneous measurement with multiple channels. That provided a new insight that there seems to be a frequency dependent damping also. So there are certain waves, they seem to be able to propagate to a larger distance. As you can see here, that there are these shorter periods, they seem to be, not being visible to very large distance. But whereas if you see these are the longer periods, they seem to be, propagating to much larger distances. So obviously, in terms of the wave propagation and carrying the energy to further out in the corona, the long period waves seems to be more important than the shorter period waves. So typically, these 5-minute period waves are there everywhere. And it was, sort of concluded that these 5-minute periods are not so important in terms of the, propagation to the very high distances and so on. So again, I'm not describing each slide to that depth, but I will be happy to answer these questions, because I'm more in the mode of a sort of global overview about the kind of studies which we have been involved. Then, of course, the question comes, what about the driver? What are the sources of these waves? So how are the slow waves generated? Where they're generated? I mean, because majority of the waves are generated in the photosphere, and there seems to be, all these waves may not be able to travel to very large distances. They get reflected, or they get damped by chromosphere or transition region. So are they generated even higher up? So these are the questions. Can flows generate waves? So this is again a new question emerged in about 6-7 years back. So we started, there were also, again, AIA made a lot of new, discoveries almost. And then these kind of small little transients, jet-like features were also seen, because AIA had much higher spatial resolution, and which were enabled to do. But then again, the imaging instrument alone cannot, conclude certain things. So I through this talk, I'm also again overemphasizing the importance of combining the imaging and spectroscopy. So there was this again, opportunity when the IRIS spectrograph was available, and there were several campaigns of joint observations between IRIS and AIA, and some of my later students, worked on this. So this is a beautiful, output from IRIS slit jaw images, where you could very nicely see the higher chromosphere and the transition region. So IRIS was dedicated for the transition region dynamics, and the beauty is it provides a slit jaw image, and also in the central portion you do have a slit, and that slit is providing you the spectral information with the standard sit and stare. So it's a combination of imaging and spectroscopy from one single instrument. So that was the beauty of IRIS. And IRIS, you can see nicely, you could see your supergranules, and you see these boundaries of the supergranules, lots of dynamics. There are all these small little jets and all these features there. Now, the question is, we can focus on these kind of boundary regions where there are small magnetic flux concentrations. We know these are quiet sun. You see, a so-called quiet sun, of course. And then we can study those, dynamics in much greater detail. So some of my later students, and this is again a classic example of how detailed, this particular frame, if you focus on, this is a example of the line profile at this point and that point, which is shown here. And we could really, study the entire time dynamics of the line profile at very specific locations on the quiet sun. So we focused our attention to this particular network boundary, where you could see very clearly the presence of the magnetic field and so on. So all these studies have to combine a imaging instrument, a spectral instrument, and of course a magnetograph as well. So in the left panel, what is shown are all these, again, the time distance map. I have not explained that probably earlier, which I should have done, but essentially it shows the evolution of the intensities, the Doppler velocities, the line width, and the asymmetry in the line profile as well. What happens is the asymmetry in the line profile also gives you a clear indication that if there is a certain jet-like features, more of a transient in nature, the spectral lines will not be symmetric. It will actually affect one of the wings of your profile. So those kind of studies we were highlighting, and that the entire time evolution was allowing us to identify where are these kind of jets, and what are the exact response of these jets to the higher atmosphere. So first you identify the location, the timing of the jets, find the connection with the underneath magnetic field, and then you find the response of these jets into the higher atmosphere. So that's the coupling of the different solar atmosphere, which is to be studied. So this is again another example of combination of observation of spicules, which you see here in the upper panel, which is stitched with another panel of IIA-175 running difference. And if you see some spicules, are generated here, and that results in propagating disturbances to the much higher layer. So these were sort of evidences almost that the spicules can generate waves as well. So this particular later paper by Tonmoy was later on followed by my Japanese colleagues, and there are lots of simulation studies which now proves that really any transients can generate waves as well, because otherwise these long period waves cannot be generated to all the way from lower atmosphere. Then, of course, you can also focus on very small little regions in the quiet sun. Incidentally, I must point out that a lot of people in the solar physics, they focus only on the flares and active region and so on. But sun doesn't produce all this activity all the time. So quiet sun provides us this opportunity to look at it at any time you like, and you find lots of interesting stuff. So I have primarily focused on quiet sun studies, most part of my career, I would say. So this is again, my later students, Chandrasekhar and then Tonmoy also looked at these are called coronal bright points. I also call them small little, mini active regions. and combining the data from different channels of AIA, IRIS, the spectral information and the magnetic field evolution. Here you see these two magnetic polarities here, and these magnetic polarities, they slowly, die out. So this is a time period where I'm showing that the bright points are still active, but then these bright points last for, hours to days. So one can study, for a very long period of time in terms of their why they're formed in the first place, how they are sustained, and why they dissipate. So that we understand more easily now because of the magnetic flux cancellation. What you see in the photosphere, eventually these bright points will die. But now, if I just focus, because this is again a spectral slit which is sitting on this, and just focus on one of the foot point of these bright point, I can study a lot more dynamics here. So again, there is a movie here. So this is what you see from Silicon 4, from Iris, and you see all these features, and nothing but shows lots of Doppler motions. That means there are clear presence of transients like these jets. So these small scale jets, now it's been also termed as jetlets, are seen everywhere. So of course, people prefer giving them different names by different instruments. Now you will hear campfire with the SDO instrument. You will hear explosive events in some other instrument, but they are all similar magnetic reconnection phenomena. The question is, what are their scales? What are their spatial scale? What is the kind of temporal scale, and what kind of energy they can contribute? How often you see them? How many you see them? Then only you can get an estimate about their energy contributions and so on. So that's the importance of this. Now I will slowly venture into a area where you combine the space observations with the ground-based observation. So because ground-based observation only gives you the best, highest possible resolution. So this is from the Goody Solar Telescope. This is done by, again, Tonmoy. And you see the granules, from the photospheric observations. Then slowly you go to slightly higher up by using H-alpha line at different line positions. And you see very clearly presence of these spicules. And the spicules are also focused in the boundaries of these supergranules. I mean, you see the clear presence of opposite magnetic polarity. These magnetic informations are also from a very new instrument in infrared. So the connection of the spicules, or the origin of the spicules by magnetic reconnection, by interaction between the opposite magnetic polarity, magnetic fields, and then you go higher up in the corona, you see the response of these jets, whether they are producing heating or not. This is an area where you could, which has been highlighted here by these boxes. You follow these jets and you see whether you see heating in those particular areas. So this was published in Nature very recently, and Tonmoy was the main person behind it. So essentially, this is what we are now doing. We are doing not only multi-wavelength, we are also trying to combine the ground-based best possible resolution data with the space-based. And this is the direction which the next generation has to take. Then only you can study the complete coupling of the solar atmosphere and study the responses and so on and so forth. Of course, there are a lot of challenges because different instruments will have different capabilities, different resolutions. So you have to understand and be able to compare these instruments when you make these cross calibrations also appropriately. More recently, I've been working a lot on the coronal mass ejections, but I will not have time to talk about coronal mass ejections today much. But I will just indicate that this is a study which Shatabdo and Ritesh, who are the two IIA students, been engaged in, and we are focusing on 3D evolution of coronal mass ejections and to find the source region. Often, the CMEs have different properties depending on where they come from. Of course, the initial acceleration and the energy which they carry will be largely dependent whether they are coming from active region or flares or prominences and so on. So this is a study where again stereo also has been used, and as you can see that there are different methods now whereby you can go back to the sun, interpolate inside the sun to find out the source region. So this is a statistical study. This has come in a few weeks back, as you can see in UpJ. And this is the profiles of the height time. So this is a slow CME from a prominence eruption. and you get the height time profile. Then you can calculate the speeds and the acceleration. As you can see here, the major uncertainty is because of the data gaps. So you have only very few data points, and this is again an area where Aditya will be completely focusing on. We will be looking at these regions where regular data is not much available at all. And with our better cadence and so on and so forth, we will be able to talk about the initial accelerations of the CMEs and so on. So these two guys are completely tuned and trained for this kind of sciences. And I hope as soon as Aditya data starts coming, they will be jumping into and producing nice results. So I will have to talk about the Kodai data, which I am quite proud of, and I am quite happy also. So this is a unique resources. In fact, this is a very classic example of, if you go back to 1st January 1958, this is a place where you see multi-wavelength data. You see, many places across the globe, people have either white light or H-alpha or calcium, but no place in the world has such an archive with all these three wavelengths available almost every day. So if you have one image per day, you will invariably find the corresponding image, because it's only by the normally by the weather, which has prevented for few observing day gaps and so on. So this is a data archive which is available in IIA's data center, and this is host a large volume of data. And as I indicated, there are 4 data series: one from calcium K, the one from H alpha, one from prominence plates, which basically blocking the solar disk. And the calcium images has been taken for the off-limb part of the corona as well, not corona, but the chromosphere. And then you can identify the location of the prominences and so on and so forth. So this, we have extensively used this data, but I'm very happy to see that almost across the globe, many people are using this data. And in coming 2 to 3 years, you will see barrage of publications using Kodaikanal data. It's already started happening, and I can update you on this. This is again, initially last 4 or 5 years, we have been working with the Kodai data alone. But now we have stepped into a phase where it is necessary to include the Kodaikanal data along with the other observatories and do the cross calibration. So I'm happy to report again. This is a new paper which Sudeep has produced, taking 13 observatories across the globe, and this is the best possible catalog available, daily cross-calibrated sunspot area since 1874. So, I guess everybody will be using now onwards this. Of course, the top panel shows the area variations. You also see double peak behavior and other features. In the lower panel, we also depict the area thresholding. What it means is, different colors represent the sizes. The red ones are the largest size, and the green ones are the smaller, the blue ones are the smaller here, smallest here. And as you can see, that the blue ones are spread over everywhere. So that's the butterfly diagram we are familiar with, but the red ones are restricted to the lower latitude. Not only that, they're restricted to mostly during the solar max. So the big sunspots, we know this, but this is a very direct representation of this way of producing butterfly diagram. In the past, I think this was not regularly done, but this is an exercise we have been doing, and this is a very important result, and I think Kodai will get a lot of limelight on this. Again, I have been working with Vidya Karak more recently, because Vidya has a lot of dynamo knowledge, and we have looked at this double peak behavior, and we have explained from a dynamo calculations also that if suddenly you have certain surges in the polar region because of the diffusion of some of the weaker fields, what is the effect you see? And that has been able to explain the double peak. I am sorry, again, I am not explaining it in detail, but these are, I thought I will just highlight. This is again a very recent work, which Vibhuti, my current younger student, is working on in collaborations with Vidya, and Sudeep initiated this work last year early. So we are looking at also the dependence of the magnetic field in terms of there are certain magnetic field or dynamo calculations they invoke something called magnetic quenching effect, which is related with the strength of the field. Again, I will not go into the details. This has come a few months back in the letter. And this is, again, a very interesting work with the dynamo community is looking at. This is primarily done from data from space, primarily from MDI and HMI, because there we do have simultaneous magnetic field information and white light. In Kodaikanal, we do not have that, but I have working out on a way of alternative to proxy the magnetic field and do this exercise. Of course, Shubham did a lot of work on the calcium 2K. This is the butterfly diagram produced from the calcium spectroheliograms. And this is, again, the area thresholding has been applied here. And as you can see very clearly, the blue ones, the small ones are there everywhere, whereas the red ones, the larger size of the plages, which will be directly associated with large sunspots, are mostly restricted to the lower latitudes. And this behavior is represented in a 3D view. I think we have not seen earlier the 3D renderation of butterfly diagram as well. There is another very interesting aspect which calcium provides, which white light do not provide, is the weaker field. Basically, here you can see that these blue ones are sort of available to very, very high latitudes as well. So these are primarily small plages, but now we can also look at network bright points, which also represents the so-called weaker field component. And there are debates about the origin of these weaker field component, whether there is a large dynamo and a local dynamo. These kind of lots of questions are there in the dynamo community. So we can address this. So this is a work which, again, Shubham did. And this is it's still controversial that whether it is 11 years or you have signatures of a slightly longer coupling between one cycle to another cycle. And this is what we have done it. We call it signature of extended solar cycle. And as you can see, this is only focusing on the network bright points, nothing more than network bright points. It doesn't include any plages. And there, if you just follow that, it seems to be that there is an overlap between the earlier cycle and the next cycle. So the cycle is just not 11 years. Probably there is some memory from this. So this is called extended solar cycle. Here, what we did, we used, of course, Kodaikanal data. We stitched or combined the Mount Wilson observatory data. And if you combine these two data, also, cross calibration, and then, some of these features are even more clearly visible. So this is something with the Mount Wilson group. They shared their data, and we exercise this, and that's a step. We are doing it now. Other interesting aspect is we have produced all these Carrington maps from calcium. We have also produced the Carrington map from H alpha. And if you combine the information of calcium, which sort of gives you indications where the magnetic field concentrations are, and if you can include the information from H alpha, which somehow gives you information about the polarities of the magnetic field concentration. Because the calcium or white light alone do not provide you any magnetic polarity information. Whereas H alpha, we know that the filaments are supposed to trace the neutral lines. So if you can use that information, then you can actually do quite a few new things. We have some work. I will not show you that result. It's just under final stages of review. Then, as I mentioned, that the prominences, which are off-limb structures that you see even for high latitudes, and these prominences been recorded from the off-limb part of these calcium disk blocked images, and there is hardly few papers, I would say, from this data. This is quite a difficult task, but we did finally succeed in this. The importance of these data is, in fact, there was a Nature paper from Kodaikanal in 1957, single author paper from Kodaikanal using the solar chart. And the solar chart gives you indications where these filaments are moving. These poleward migrations are very, very important in terms of the dynamo calculations, because these poleward migration dictates the strength of the next cycle and also the timing of the next cycle. The faster these these migrations to the pole takes place, of course, the polarity reversal will also happen based on that. And what you also see is that often there are signatures of multiple polar rush as well. So this is a new thing which we are seeing from magnetic informations with the recent few cycles, and then we are going back to the past history and we are discovering the same thing. So here again what you see is the Kodaikanal data. Then we included data from Medo and Kanzelhoe, and we see similar features. And then if you combine all these three, then you can get these poleward migration rates. And these poleward migration rates I have shared with some of the Dynamo colleagues in the West, and they're very happy to put it in their models to talk about when the new cycle will begin and so on. So in summary, this is a recent work of the Kodaikanal digitized data set from H alpha, calcium, and white light. These are some of the publications which are listed. We have done from plage detection Carrington maps, long-term variation in the intensity of the plages and the network. We have also worked on supergranular detection, the temporal evolution of the active and the quiet sun. We have also worked on supergranular scales, whether it varies with the different solar cycles. So those are some of the things which from the calcium extended solar cycle, for example. And then from the white light, there are multiple work as well, as you can see. And most of these, I'm very happy to report here, all led by our Indian younger colleagues as well. Here you see Sudeep, Shubhamay, Muthupriya, who was there in the digitization project initially, and she has contributed also. And then Manju, more recently, been into the project. But I must mention one person who is the most probably quiet and most active, quite active person in IIA. And digitization project, of course, in my duration has been largely because of Ravindra. He's probably the I do not know how to describe him. I was trying to search his image in the web, and there are not many places he's visible. So finally, I managed to get it from somewhere. So he's always working very hard in the background, but he's probably the most effective person in terms of any project. So I'm really thankful. Thanks Ravindra for supporting this program for such a long period. Of course, I must admit, this program was handed over to me much later. All these started by Professor Jagdev Singh, and this was a mammoth effort. He built the digitizer unit. He initiated all the digitization process, and probably we are all getting the fruit out of this now because of his efforts, what he initiated at that point of time. And again, a lot of credit or sort of acknowledgement has to be there with Professor Siraj Hassan as well, because he wholeheartedly supported this program in a big way too. And I think it's not a bad exercise, at the end of the day. So this data is very widely used and very publicly available. This is my earlier gang of students here you see here. But then I will talk about again a little bit of history. I will go back. I'm getting nostalgic to go back to my earlier days. We enjoyed our life like anything. I must say, IIA is a great place to work, and IIA has nurtured us and pampered us like anything. And we have been given this opportunity to go around, do whatever we like. I don't think you will find that opportunity in many other places across the globe. I must confess that. And I think the younger generation should value that. I mean, I am indebted to that. I feel very obliged today. I have not tried to say no to anything which my institute has demanded from me, but I feel privileged to do this. So this was a unique experiment. This is solar eclipse, October, and then we were selected to go into this AN-32 aircraft. Me and Krishna Kumar, another younger student, and Mr. Ramani was actually with us. And we had a fantastic solar eclipse viewing. So I will share some pictures of solar eclipses. This was a next expedition to China, 2009. And this was a very successful eclipse expedition. And then, of course, you see that we had two DFM telescopes there and the spectrographs there as well. two simultaneous observations in red and green line. Incidentally, some of the data which we collected during those eclipse experiment and the one which I will show you later has been the, sort of core data for Aditya calibrations and understanding. So this is again, all the eclipse expeditions, I must say, is again led by Professor Jagdev Singh. Without his leadership, I don't think this expedition should have continued, and it has not continued because probably of his absence as well. So I must confess that we have not been able to continue this eclipse expeditions anymore. So it was a combination of these two DFM telescopes. One is in Kodaikanal, one is in Meerut now, but it has been used extensively, and we are still using that data for Aditya purpose. So this is the camp. I was busy, taking this data inside the tent. Couldn't have time to see it with my own eyes, but this is the spectral lines, which was a single slit experiment, which was repeated in the next eclipse. Again, not many people get this kind of luxury to go to Chile, and that to Easter Island, one of the remotest place on the earth. So again, it all happened because of IIA, and of course, it's our duty to make use of that and do the requisite science. This is the beautiful island, and you see these statues which are famous all over for its history. Even the Indian ambassador who was in Chile, he flew into the Easter Island and observed the eclipse with us. Again, this was led by Professor Singh. And I must admit, again, another big gentleman which we miss is Mr. Gabriel. He is, I'm here in Aries, and I hear every other day, how good Gabriel is. He has helped here as well people to set up a lot of things. And we sadly lost Ravi, but he was also very, very smart, in this experiment. So this was a more recent experience from Argentina last July. It was not part of any eclipse expedition. I went for attending a solar conference and was fortunate enough to be in one of those hills here. This is not a movie taken by me. This is taken from plane. You can see it. But we could see this eclipse, beautiful eclipse from these mountains. This is taken from Chile side. I was there in the Argentina side. That's in the other part of these hills. So that's again fantastic. Future, of course, multi-wavelength, multi-site, combining space and ground. And I think India is really getting into a major leap, a change in terms of the solar observing facilities. And for the next generation and the current solar students, I think this is dream come true. I mean, we couldn't dream, I think 30 years back, that India will be able to host such things. So combination of Aditya L1 and NLST, I think we will take to the next generation. I'm preparing for that. I have a good bunch of, again, students. So as I said, that, this Guru Shishya Parampara, as I started my statement, that whatever I learned from my mentors, a little bit, whatever I could digest, I'm trying to, pass it on to the next generation. And I'm very, very, proud of my students, because they're bright, they're good. But I think all of them have to, think about, how to value the opportunities they're getting. The future is very bright. So this is, I will not go into the full details of what all they're doing, but most of them are related with Aditya science, and some are involved with, of course, the Kodaikanal data as well. We have few postdocs as well here now in Aries. So I must tell you that IA has provided a platform for doing a lot of things, whatever you like. My son took this picture, half an hour back. I said, don't you want to say about, sports? It's true. I was the, football team member of ISC for 6 years during my PhD period, and even captain for a couple of years. And I participated in all kinds of sports activities within IA as well. Still, some of these are there on my, the top of the cupboard. It's there in Bangalore. It's not with me. So my son took this picture and sent me. I try to do this here as well. So immediately after I joined here, so I took part in the cricket team. but unfortunately, it was not possible to continue this. But this is a beautiful place. This is a wonderful place, and this 3.6-meter telescope is really, really out of the world. And the sight, what you see, the Himalayan range in the back, is really, really mind blowing. So, again, I just wanted to say again and again that how fortunate I am to get this privilege, and my journey has been always enjoyable, and I have enjoyed every part of it. The future solar physics lies with these bunch of guys. Uh, we had a solar physics school in our Hanley guest house last year only, and I'm looking forward to these bunch of people to take things forward. Opportunities are there, and this is my recent sort of gang. Not all of them are here, but this was again taken last summer when we were in Hanley. So I'm still waiting for another opportunity to interact. So again, thank you very much for giving me this opportunity. I see that we are privileged in this difficult time. We are still having fun and are able to manage our shows. So I think we should value the opportunities which we are given. And I again thank IA for providing this platform. I really, really am indebted to it. Thank you for your attention.
Thank you, Dipankar, for a very nice, interesting talk. You will be able to take some questions now.
Sure, sure. Happy to.
Yeah. So, questions?
Let me know if I should stop sharing or let it be, and I can because I don't know who is posing the question probably otherwise, but I'm okay with either way.
So, are there from the participants? If there are no questions.
Yeah, Dipankar,
Yeah.
it's a nice talk. So, just wanted to ask you one. I mean, of course, there are many things which just went above my head. Can't understand too many details, but can you just tell me one particular scientific aspect which you will try to understand or throw more light on regarding the sun, which is one of the key questions in the
Okay.
next 5 years?
Okay. So yeah, of course, the problem of the coronal heating is almost I would say solved, but the solar wind acceleration is still not fully understood. So since there is a coupling between the different layers of the atmosphere, you really need to understand the source region and the effect. So a combination of observations or models which includes different layers of the atmosphere. Maybe this is a picture which sort of depicts the picture. You have certain dynamics here you see in the lower atmosphere in terms of the magnetic field changes, and because of these changes of the magnetic field, what is the response which you see in the higher layer in the atmosphere? That will tell you the story about the energy and the wave propagations and so on. So that is something which I have looked at in a shorter time scale. So again, sun varies in many different time scales. So there are changes which takes place in terms of seconds to minutes, and then there are certain changes which takes place in hours, and there are certain things which are in terms of years or millennia and so on. So of course, different physics is involved in explaining these kind of changes with time, in that context. Of course, for everything, it appears it's a magnetic field which plays a major player, it's a major role, in changing these dynamics. So you need to understand the magnetic field evolution, first, and then you see the response of it.
I have a question. Dipankar, it's Jayant here.
Yeah.
I'll ask you the same question I asked Siraj, and you had some comments on that then also. Where do you see, how do you see India making the next leap into solar physics, considering the manpower issues, considering the student issues, and this year considering the money issues? Where's the next leap going to come from?
Yeah. So I would say definitely the next leap is Aditya, because Aditya has a set of instruments which other satellite missions do not have. So, but these are difficult instruments. One need to understand the capabilities of the instruments. But I must also tell you, fortunately, the younger solar physics community is not too small now as well. As compared to our times, this is much, much healthier. So that way, I am quite hopeful that Aditya will pave a new way. The other thing is, most of the other space data is anyway in the public domain. They're always available. So combining this, Aditya's capability with the other, observatory data will shed definitely some new light. Of course, it would have been ideal to have the NLST also in synchronous time. The synergy would have been perfect. But as you rightly pointed out, the financial situation, I don't think will allow us to get the NLST very soon. So we have to wait for that. And the ground-based observational facilities, what is there in India now, will only provide a context. I don't see that it will be able to provide, a sort of path-breaking, new element there. Yeah.
Okay, Dipankar.
Yeah.
There are two questions from this YouTube channel. So can I read out
Sure.
this?
Sure.
Yes. So the first one is, it is asked by somebody called Vijay Kapoor.
Mm-hmm.
So the question is, currently, sun is going in least active period. I
Mm-hmm.
read in some book, quote, when a solar spot emerged on upper northern hemisphere of sun, then another solar max cycle starting soon, unquote. Is this true and why?
Yeah. So it's a very good question, and so I think the speaker is right that we are undergoing through the solar minima, but we have just started seeing some new sunspots. So there is always an ambiguity to characterize that sunspot whether it belongs to the old cycle or to the new cycle. So it looks like now there is a clear indication that the sunspot which are very recently appearing on the surface of the sun is coming in the or belongs to the new cycle. So what happens is, for the previous cycle, when the sunspots, there are two migration what happens. That is the explanation of the butterfly diagram. The sunspots move to the equator from the two opposite hemisphere. So when they approach the equator, then flux cancellation happens, and then you have the minimum, so no sunspot appears. But then when a new cycle come, then there is a prevalence that there is a preference for the north side as well, and then there you start seeing a sunspot into slightly intermediate latitude. So that's the because of course one needs to explain the flux tubes or the sunspot which comes from underneath the sun because of the magnetic buoyancy force and because of the Coriolis force, what latitude it should appear in the new cycle and so on and so forth. So that all is reasonably explained from the flux transport dynamo models. So we understand from those models the global behavior, and the new sunspots appear at certain latitudes as well. I hope that satisfies the query. Yeah.
He has one more question.
Yeah.
So how can amateur astronomers with H alpha telescope setup can help in any research program for IIA?
Okay. Yeah, probably Ravindra will be a better person to answer this. But generally, any H alpha telescope, in fact, in Aries also, we do have a H alpha telescope. Its only difference is this is with a larger magnification, so it looks at only a small portion of the sun, whereas the telescope at IIA is looking at the full sun. So there is, of course, one particular setup where you can zoom over a smaller portion of the sun as well. That particular H alpha telescope has that feature. So if somebody is interested in looking at some of these dynamic events like flares on the sun, then one can participate in those kind of exercise. One can make flare catalogs, and then some of the flare properties, how strong these flares, and then they can. A lot of data is available these days globally in terms of the flare properties from other places as well. So one can just combine this. So I guess one can participate in a voluntary mode if they are interested, but one needs patience the sun doesn't always listen to you, and but you may have to wait for months before a flare is observed. So that kind of patience is also required.
Are there any more questions? Okay. So if there are no more questions, then let us thank Dipankar for a very interesting talk. With a lot of nice pictures, memories. Thank you, Dipankar. Thank you, all the participants.
Thank you.
And with this, we will end this meeting.
Thank you.
Thanks, Dipankar.